In lecture 15, we're going to do something very interesting, and we're going to prove the fundamental theorem of algebra. Let's just recall what the fundamental theorem of algebra says. Now, algebra often means polynomials. Not always, but a lot of the times it means polynomials. When in universities you have these introductory algebra courses, so not like the abstract algebra courses, but like the introductory intro math algebra courses that a lot of people have to take, then the reason why they call them algebra is because most of everything you do in that class are polynomials. So you have factoring polynomials, finding roots of polynomials, graphing polynomials, rational functions, how to add two rational functions, but a rational function is a polynomial. And then even when you have equations that look like they're not polynomial equations, but they are in disguise. So like when they do something like solving an equation involving sine and cosine equal to something else, you basically realize that you can convert that by a Pythagorean identity. And then when it's written entirely in cosine, so when it's like something like this, you're basically making a substitution, and then you have y squared plus y plus some extra stuff. So trigonometric equations get converted to polynomials, exponential equations get converted to polynomials. So basically, it's an entire class of just polynomials in disguise. That's really what it is. So that's what algebra is. And the fundamental theorem of algebra, it's sort of the main theorem about polynomials. So let's just say what the theorem says. It says that, so theorem, and the first person who proved this theorem was Gauss. He was the first one who proved it. This is something that many people have suspected for a long time, but Gauss was the first one to prove it. So the theorem says that if f of something, let's call it f of z, is a n z to the n plus a n minus 1 z to the n minus 1, so this is a polynomial, a1z plus a0. So when you're using powers of a variable, we call that a polynomial. And it says that if the degree, so you're going to assume that the degree of f of z is at least 1, the degree of the polynomial. So you're not going to have something silly like f of 3 is equal to 3. This has degree 0. There is no z in there. So you at least have a z in there somewhere. So then it says there exists a complex number, let's call it z0, so that f of z0 is equal to 0. So there exists a complex root. So you always have a complex root. And what makes this theorem surprising is that complex numbers were introduced to only solve quadratic equations. That's why they were introduced. So when we talk about I squared being equal to -1, that is the solution to the equation z squared is equal to 0. You have quadratic equations that are not solvable using real numbers, so you have to introduce a new number, which you call I, and it allows you to solve quadratic equations. So complex numbers were introduced to solve quadratic equations. And then the amazing thing happens that if you have a cubic equation, or an equation of degree 4 or degree 5 and so on, you can always solve it. So for example, the equation, let's say z squared, z to the 4 plus 1, z to the 4. So maybe some of you have seen this before. This is related to like roots of unity. So here, how would you solve something like this? Well, I'm just going to tell you what it is. So minus 1/2 plus I squared of 2 over 2. I think this works. I think that's going to work. And I think the other ones are, it's actually, I believe it's actually plus or minus. So you get 4 roots here, and you can either choose them to be both positive, both negative, plus, minus, minus, plus. I think I'm just kind of going off by looking at it, but if I'm not correct, then I'm close to being correct. I mean, the point is that this equation, you would think, oh, you need to introduce something new because now it's being raised to the power 4, but it's actually solvable. And all equations are solvable using complex numbers. This is what makes it super surprising. And what makes it hard to prove, the reason why this is very hard to prove, is that there is no general formula for solving all polynomial equations. Like if you had some kind of nice simple formula for solving any polynomial equation, then you could just look at the formula and say, there it is, that's how you solve it, that's how you find z. But this is like one of those situations where you have to be able to assert that something is true without having a formula to do it. And the way the story goes, that Gauss found a proof of this, and then he found 3 more proofs of that, because one proof is not enough. And we're going to show a proof using topology. And the interesting thing about this proof is that I think this is actually very close to the way Gauss did it. The simplest proof, so there is a one-liner in complex analysis. So if you take a course in complex analysis, if you've ever taken a course in complex analysis, there is a one-liner proof of this. Though, to be fair, every proof is a one-liner if you make the font size small enough. So, but I mean, even with normal font size, it's a one-liner. But in a way, it's kind of cheating, because by the time you get to the proof of this theorem, you've done like 200 pages of complex analysis. Like you know so much about complex analysis that you can just take advantage of that and prove the theorem. If you actually had to prove the theorem from first principle as well, it's going to be quite long. And Gauss's proof, I think, was 27 pages long or something like that. And it was so long because he was basically trying to prove it from first principles. And the proof that we will present will be very short. And in a way, it's only short because we've done a lot of the previous work that makes it possible. If we've never done the previous work, then we would have to justify the things that we're saying. So Gauss's original proof, I think his very first proof, is topological in nature. And what he had to do is he had to take all of that intuition that he had, the pictures that he was seeing, and convert it into more rigorous mathematics to justify what he was doing. So now, before we give a proof, let's give the idea behind the proof. A very nice idea. And I think this is harder than the proof. You can, of course, always look up the proof somewhere, but there's a difference between understanding and knowing. If you look up a proof and you go through the proof and you verify it, then you know that it's true because you just proved it. You know that it's true. But understanding something is more than that. A lot of the times when you read a proof in a book, you can check it, you can go through it, but you don't really understand it because you look at that and a lot of the lines are very mysterious. A lot of the lines are unclear, like what was going through the mind of the author to write something like that. A very common feeling is when you see something in the book, you think to yourself, well, how would I have came upon that idea myself? So what we want to do now is we want to discuss the idea behind the proof, and then we will show the proof. So here's the idea behind the proof. So you have a polynomial. You have a n z to the n. You have a n minus 1, z to the n minus 1. So you have these coefficients. They could be complex coefficients. It does not matter. So this is your polynomial. And Gauss said that this is the most important term. This is the dominant term. That's the dominant term. That's the one that matters the most. So as you go off to infinity, as z gets larger to infinity, this is the one that matters the most. So the idea is you're going to draw a circle in the complex plane. And you're going to draw a circle with a really big radius. Right? The radius of this is really big. Really big radius. Now, what do we mean by really big? This is vague, right? This is not the formal proof yet. This is just the idea behind it. You're going to blow up the circle big enough so it's really big, and big in the sense that when you're located on the circle, this is the one that matters the most. These ones have very, very little effect. So the size of this radius will depend on these coefficients, the degree, and all of that. So if you make the radius big enough, then if you want to know what this polynomial, so this polynomial is sort of like a function, what is it doing on points in the circle? This is the one that matters the most. The other ones have a very minor effect. So f, so it's a function from the complex numbers to the complex numbers, but let's see what it does to the circle. So we visualize the complex numbers as a plane, and what does f do to the circle? Well, this circle, so what's the equation of the circle? So let's say the radius, so let's say you can describe the circle as r e to the 2 pi I t. It's a loop. It's a closed loop, and if you let t vary from 0 to 1, then the radius stays as r, and you move around the circle. Now, what kind of effect does this function have on the circle? Well, let's put it in there. So in fact, you would have f of re to the 2 pi I t. And remember what we said, we're only going to look at the dominant term. In fact, maybe we can even pretend that an is equal to 1, not to really pit. I mean, it does not really matter. Just pretend it's equal to 1, because you can always rescale. If this is 5, you can just divide everything by 5. So you can just pretend it's 1 or something. Does not really matter. So this is the dominant one. So what happens when you put it in there? Well, then this is z, and you put it in there, so it'll be that raised to the re to the 2 pi I t raised to the n, and then you have other terms. These dots represent the other less significant terms. So what is this? So when you open this up, this is r raised to the n, and this is e to the 2 pi I nt. This is 2 pi I nt. And then you have the other terms that are less important. So what happened to the circle? So the radius, it exploded by r to the n. So it got even bigger. But what happened with this term? This term was 2 pi I t, and it became 2 pi I nt. So now you're going around n times around the circle. So let's draw this. So let's just draw another circle. I'm not going to draw it any bigger. I'll just draw it like the same size. But we understand it gets even bigger. Like this r is some big number to make all of the terms insignificant. And then what is this? This is when t goes from 0 to 1, nt goes around n times. So this is sort of wraps around the origin n times. So, but you see, it's not actually going to look like this. You have the other terms. So in actuality, what's going to happen is, I mean, you can do this with examples on a computer. You can like draw pictures on a computer, take different polynomials, put different circles in them, and you will see what happens. It's basically like this circle, but then you have small little perturbations along the circle. So the actual image, it's going to go something like this maybe. It's going to go around like one time, maybe something like this. Then it'll go around like a second time around it, and then it'll go like a third time. So if the degree is 3, then it'll go like 3 times around it. And if the degree is n, then you'll have like this loop that's going around n times, but it's mostly staying in contact with this red circle because that's the most dominant one. The smaller terms make small perturbations around it. So that's the idea. So this is what Gauss said. He said that look at this image circle, and what do you notice? You notice that it contains the origin. It contains the origin. So the image circle winds around. It contains the origin inside it. The origin is inside this loop that's going around. You have some kind of winding number, and that winding number is going to be n because you're going around n times. The winding number is going to be n. You're inside there, so you have some kind of winding number. Now, where does the contradiction come from? So the contradiction comes from, you assume, so Gauss said that assume that this polynomial had no root. So there was no root anywhere inside that circle. So you assume that there's no root. So far we have no contradiction. So you assume that there is no root within this disk. This polynomial does not vanish anywhere over here. Then the picture will look a little bit different. The way the picture is going to look like is you're going to transform, that this is going to be your mapping. This is your mapping F. What is it going to do with this disk? Well, it's going to transform it, and it will stay away from 0. It will never be equal to 0 because you're making the assumption there's no root. And you'll end up with a region that's something like this. That's what you're going to end up with. So that's what you're going to have. But then what do we notice? We notice there's a problem. If you look at the boundary that is now being formed around this region, you would say the origin is outside the region. But here, the origin is inside the boundary circle. So that's where the contradiction comes from. That the picture is supposed to look something like this. So whatever the circle is, it's supposed to get mapped to something like that. It's supposed to have 0 inside of it because this is sort of the boundary circle, and that's inside the region. Whereas here, if you assume there's no root, then that's the origin, and it's not containing the origin, and so when it gets mapped to something like that. And now you have a contradiction. These two pictures are in conflict with each other. How can 0 be outside the region, And then how can 0 be inside the region? And that is the contradiction. And that is essentially the picture behind it. It's a very interesting idea. Now, what makes it difficult is how do you make it rigorous? How do you make this precise and all of that, right? Without using pictures or anything like that. So that's the motivation behind the proof of it. But how do you make this work? And this is what Gauss put in a lot of work trying to figure out how to make it rigorous enough so that it is a fully proper mathematical theorem. And Gauss did not have access to topology back in the beginning of the 1800s, though he probably figured out a lot of it on his own. But we do have access to topology, so we have better tools that will enable us to solve this type of problem. So here is what we're going to, so here's the proof that we're going to do. We're going to use our knowledge of the fundamental group to make this work. But I have to give you a warning, and maybe some of you are going to be bothered by this. Our proof will have a minor flaw in it, but I'm not going to tell you. I'm not going to tell you what that flaw is. You'll have to figure out the flaw yourself. And you can think of it as an exercise to figure out what the flaw is. And the flaw could be fixed. The easiest way, the easiest method for fixing this flaw will be to use something called homology. At the moment, we're using the fundamental group. We're using holotopy. But there's something called homology. And homology will fix the flaw. And then if it bothers you, if you figure out what the flaw is and then you have this psychological problem that it bothers you that there's an issue with the proof, you can just wait until topology part 2, learn about homology, return back, and you'll be able to fix it in a very straightforward way. The idea will still be there. Or you can always look at Muncre's. Muncre's does it differently. But the way I like to present this proof is in the way that's intuitive, in the way that when you look at the proof, in the end, it makes sense. It makes sense, all of the steps that we did. Sometimes when you look up a proof in the book, it might not be clear why it was written in that particular way. And this is sort of the approach I have to mathematics in general, that sometimes it's okay to have a minor flaw or something that's incomplete in the argument if it leads to a better understanding. Because ultimately, what we care about is the understanding of what we're doing. That's much more important than having absolute perfect rigor, because we can always write everything perfectly rigorously with no flaws at all, but if people are lacking an understanding of it and we're not fully understanding what we're doing, then that is not as beneficial. So let's therefore show how to make this proof work. So we're going to assume, so let f, instead of f, let's call it p for polynomial. So let's say our polynomial is going to be, so the main coefficient in front is going to be 1, and then you'll have other coefficients, plus a n minus 2, c n minus 2. So this is our polynomial. Okay, so that's our polynomial. And I should say that the flaw is so subtle that maybe if I never even told you there is a flaw, you would have never even noticed it. But it's a good way to review the things we've been talking about. So anyway, this is our polynomial, and we're going to assume that this one is dominant. So dominant in what sense? It means that these coefficients are small in comparison to it. So dominant in the following sense, that the sum of these coefficients in absolute value, so they could be complex numbers. So they could be complex. But regardless of whether they're complex or not, you have the absolute value of a complex number, and the sum of these are all less than 1. So they're all pretty small in comparison to the one in front. So this is like 1 in front, and it's sort of more dominant than the other ones. Some of you might be thinking, but what if the polynomial does not fit this description? Oh, that's not a problem at all. You can rescale the variable. You can replace z by z divided by some constant, and you can just rescale everything and bring it back to this kind of form. So that's not very serious. So we're going to make this assumption. And now we're going to first show, okay, not yet, and let f be the mapping from the closed interval into the circle. That is the mapping we've been using many times. F of t is equal to e to the 2 pi I t. So this is the generator for the fundamental group. So this is the one that wraps around the origin one time. So this is our loop. So this is our loop at 1, right? If t is 0, and t is 1, f of 0, f of 1 is 1. So this is a loop at 1, and this is, of course, a point on the unit circle, because 1 can always be written as 1 plus 0i. So this is a point on the unit circle. Okay, and we're going to do the picture that we did before, that we have our loop. So that's our loop, and then we're going to apply to that loop, we're going to apply the polynomial. Okay, we're going to apply the polynomial, and we get out of this some kind of other loop that will probably go around like n times or something, because you have z to the n. So you're putting that, so this is going to be the loop. So now you have a new loop. Let's call it, for lack of a better name, let's call it g. This is I into, so I guess, yeah, so this is into the punctured plane, into the punctured plane. Let me also write this. Let's assume P of z has no root. It has no root. So we're going to get a contradiction somewhere if we assume it has no root. So we assume P of z has no root. So that means, so I'm going to show you how this loop is being defined. So the way this loop is being defined is, it's g, you're just composing with the polynomial. So it's p evaluated at e to the 2 pi I t. That's what it is. E to the 2 pi I t. So you're composing, you're basically taking this loop and you're putting it into this loop. You're putting it into the polynomial, and you get the image loop. This is the image loop. So this is what you get. And the picture that we had before is, if this goes around and you put it into the polynomial, then z to the n will make it sort of wrap around n times, and you'll see like these n different circles kind of going around the origin. So you have this. So this is your new loop. And we're going to argue, so we will argue, okay, so we have this loop, and then we have another loop. And we also have the loop, let's call it h, that maps I into the punctured plane, and this one is given by h of t is equal to e to the 2 pi I n t. So this is just basically, this is like the first dominant term. This is basically e to the 2 pi I t raised to the n. So this is essentially putting this into that dominant term. So this one, so the way this loop looks like an actual, well, this is an actual circle. It's not going like that, but it's sort of going around itself n times over itself. And we want to show that these two are homotopic to each other. Okay, so we claim that, you see, we want to somehow argue that this loop contains the origin inside of it. And this one contains the origin inside of it. So it has something to do with winding numbers. That you can use winding numbers or you can use homotopy, because they're equivalent. If you recall, last time we said that two things have the same winding number if they have the same homotopy. So one way of showing that 0 is inside it and this goes around n times is by computing the winding number and showing it's equal to n. But you can also show that this thing is homotopic to this one, and we know the winding number of this loop is going to be n. So then 0 is going to be inside, and it winds around at n times. So we claim that G and H are homotopic to each other. So we construct a homotopy. We construct and we use this many times already, the straight line homotopy. The straight line homotopy. So this is, let's call it capital H for homotopy, because we're already using lowercase h for a loop. So we're going to have I cross I into the complex plane. So this is the time parameter and the interpolation parameter. And the way we're going to do this is we're going to write h of t comma s is going to be equal to 1 minus s times g of t plus s h of t. So now you can see that if you set s is equal to 0, this goes away. So if you set so h of t comma 0 is equal to g of t, and h of t comma 1 is equal to h of t. So hence h is a homotopy between the two loops, g and h loops. So these two loops are homotopic to each other. Now, the one thing that you have to check, I'm not going to check this. And by the way, this is not where the mistake occurs. It's not where you have to check. You see, you're claiming that this is a homotopy in the punctured plane. It's a homotopy in the punctured plane. So you have to argue that this is not equal to 0. So you need to show this is not equal to 0 for any t and s in the unit square. You have to show that. You have to show that this is impossible. And this is where this condition comes in. You have to use this condition on the coefficients, because the coefficients of the polynomial, you see, basically the idea is this. These coefficients are smaller than 1 when you add them up. So this is sort of like smaller, sort of like smaller than 1 over here. And then you have to argue why it's, well, you basically have to do this. You have to say that if you equate it equal to 0, and then you argue why this is impossible. And essentially what it's going to come down to is, because these coefficients are smaller than 1 in absolute value, by playing around with the triangle inequality, you're going to show that this will never be equal to 0 for any choice of t and s. So in particular, you have constructed a homotopy in the punctured plane, okay? Because these are loops in the punctured plane. We're working in the punctured plane. So this is a loop in the punctured plane, that is a loop in the punctured plane. So when we construct a homotopy between those two loops, it has to be a homotopy in the punctured plane. So that's why you kind of have to check through this. Okay, so that means that G and H are homotopic, right? G and H are homotopic. So what does this mean? So you can say, so thus, you can, if you want, you can use winding numbers. So you can say, so thus, well, so thus this. So thus G is the same homotopy class as H. G has the same homotopy class in H. And what is H? It's this raised to the n. That's F raised to the n. This is the loop that we started with, right? This is sort of the main homotopy class in the fundamental loop. So it's F to the n, okay? So you can say, if you want to, in the notation of winding numbers, you can say that the winding number of G is equal to n. It's equal to its degree. So you can say that if you want to, because the winding number is determined by the homotopy class. But then that's the same thing as just saying, it's just saying it's the same homotopy class as F to the n. Okay, that would be the first step. Now here's the second step. So that was step 1. So now we assume that the polynomial has no roots inside the disk. Okay, so we have our unit disk, and we assume there's no root. This polynomial never vanishes. So we will construct a homotopy from G of t, from G. So what is G of t? So G, this is the path, this is the closed loop, which was e to the 2 pi I t. That was the closed loop. From this and a constant path. A constant path. So this is where the contradiction is going to come from. That previously in step 1, we argued that G was homotopic to F to the n, so it had winding number 1. But now we're going to argue that G is also homotopic to a constant path, and so its winding number is going to be 0. And those together will give you the contradiction. Okay, so how does one do that? So you're going to construct the homotopy. I'm going to call it H again. So this is I times I into the punctured plane. and it's going to be defined as follows. It's h s e to the 2 pi I t. Now notice that if s, well, we usually put the t first, not that it really matters. The t goes first. So if s is equal to 0, then this is just the origin. If s is equal to 1, then e to the 2 pi I t is on the boundary. And if s is some number between 0 and 1, let's say s is a half, then a half e to the 2 pi I t, this is just the circle in the middle. So you're just filling in. You see, you're just filling out this disk. You're just filling out that entire disk. That's what you're doing. So whatever this is, h of s e to the 2 pi I t, this is when s and t, they range over the interval from 0 to 1, they just fill in all of the points in the disk. And it's being mapped to the punctured plane because by assumption, it has no roots inside the disk. It has no roots. Polynomial has no roots. So because it has no roots, none of these points that are inside the disk are being mapped to the complex numbers, right? That's the assumption right there. And that's where we're going to get the contradiction. Now, this is a homotopy between what and what. So now, so observe that h, okay, this makes no sense. I just realized it. It's not h, it's p. It's the polynomial evaluated. And if h of ts is equal to that, that's what I meant. It's the polynomial that's being evaluated at that. So now observe that h of t comma 0 is equal to p of 0. And p of 0, that's just the final term of a polynomial. It's just this. So this is a constant path at a0. That's just a constant path. Because no matter what t is, by setting s is equal to 0, it goes away, so it's p of 0. So it's just putting 0 into the polynomial, and then you recover the initial coefficient a0. So that's just a constant path at a0. And if you set the other one, if you set h t comma 1, then that's going to give you p of e to the 2 pi I t. And that is exactly what we're calling g. That's the loop that we're calling g. So that's g of t. And this is a homotopy. This is a continuous map. This is continuous. Polynomials are continuous. That's a continuous map. Right? We're being sloppy. We're not actually verifying they're continuous, but it's believable. It's continuous. So this is a continuous mapping into the punctured plane. So what does this mean? So hence, h gives us a homotopy between g of t, right? I'll just call it between the loop g and the constant loop a0. So the constant loop, this is just the loop that stays at e0. So thus, g is in the same homotopy class as this constant loop. I guess we sometimes write it as the constant loop at a0 if we're consistent with our notation. So if you want to use winding numbers, you would say the wind of g is 0. The winding number is 0 because this is homotopic to the constant loop whose winding number is 0, and that's the contradiction. In the previous line, we saw that the winding number of g was n, and now it's 0. And so we have a contradiction out of this. So that's the question. I'm sorry, that's the proof, not the question. So that's the proof. This is the contradiction. And so it means that the way you avoid the contradiction is that this is not a valid homotopy in the punctured sphere. So that means there has to be a root somewhere inside of it. So that is the fundamental theorem of algebra. That's the way you prove it. If the winding number stuff bothers you, you do not have to use winding numbers. You can just use homotopy classes. So you've shown that G, this is the identity homotopy class, and then here you've shown that G, this is the homotopy class of F raised to the n, which is not the identity class. And that's the contradiction. So if you do not want to use winding numbers, if that for whatever reason bothers you, you can just do it using this. And you see, this is what we've proved last time. Last time when we talked about the fundamental group, it really comes back to the fundamental group. The fundamental group of the punctured plane. We've said that it consists of the identity one, then it consists of f, it consists of f squared, it consists of f cubed, and so on. And it consists of negative powers of f as well. So this is the complete list of all homotopy classes. So the reason why we know that this is not the identity class, the reason why we know they're actually distinct from each other is because that's what we proved last time. That's how we're using the work from the previous lecture to make this work out. So that's the fundamental theorem of algebra. That's a very nice proof. So now I want to show you something else, something unrelated, something totally unrelated to the fundamental theorem of algebra. And it's something that's also very interesting. It's called Brouwer's fixed point theorem. Very surprising theorem. So before I tell you what Brouwer's fixed point theorem says, I want to begin with this simple version. So this is the 1D version. And you can prove this using basic calculus. So you can even prove this in calculus 1 as a challenge problem. So it says this, that if f is a continuous map from the unit interval to the unit interval, continuous map, then there is a fixed point, i.e., you can find some point in the unit interval so that f of p is equal to p, a point that does not move. That's what we call a fixed point. Fixed point has to exist. Now, if you draw this as a picture, it's somehow believable why it always must happen. So the function f of x is equal to x, it's this line right like this. That's the function f of x is equal to x. That's the line, right? F of x is equal to x. F of x is equal to, that's the line. And this function that we have, maybe I should not write f of x because it's confusing. Yeah, maybe I should just say that this is like y is equal to x, and then y is equal to f of x. That's the other one. So it does something. I do not know what it does. It does something. Well, you see, whatever this function is doing, it's defined from 0, 1, and it has to stay within this square. So you can see that no matter if you start it somehow here, it has to cross. Like if it only stays on this side, then the fixed point occurs at the end point. And if it crosses downwards, then at some point they cross, and then you have f of x is equal, like f of p is equal to p. And if it starts down here, that's sort of the, well, it cannot start down here. It has to start somewhere on the left. So it either never crosses and it kind of meets at that point, or at some point it crosses, and then you have your fixed point where the two intersect. So when you draw pictures like that, it's pretty believable why that works, but you can prove this. So it's going to be an exercise. You prove this using the intermediate value theorem. It comes down to the intermediate value theorem. And you can even prove this as a first semester Calculus 1 student. So if you're like a talented first semester Calculus 1 student, then you can handle these more theoretical type of problems and then prove it using the intermediate value theorem. So this is like the one-dimensional version. Now, the same thing works in 2 dimensions. So this is like Brouwer's fixed point theorem. The same thing works in 2 dimensions. So this is the 2D version. That's the theorem that we're about to write down. This is Brouwer's fixed point theorem, and this is the 2D version. So you have to replace this closed interval by, now you could replace it by a square, by a unit square, but topologically you can either use a unit square or anything homeomorphic to the unit square. So we're going to use the closed disk. So D2 to D2. This is the closed unit disk. So this is the closed unit disk. So it says that if you have a map from the closed unit disk to the closed unit disk as a continuous map, then there is a fixed point. You can find something in the closed unit disk so that f of p is equal to p. And that's what we're going to prove. And the intermediate value theorem cannot be used here anymore. Intermediate value theorem, that's for single variable calculus. So I have to do something totally different. And here's like an interesting consequence, an interesting, surprising consequence of this theorem. So imagine you have a bowl of soup, right? So this is a disk, right? A closed disk, right? The surface of the soup is a closed disk, and you take a spoon and you mix it around. So you're basically doing a mapping from the disk to the disk, that after you mix it with the spoon, things move around, so now every point goes to a new point. And what we're saying is there exists at least one point in the bowl that did not move at all. That's like the surprising thing. So like, for example, you can even visualize this in like a real life experiment. So imagine that this is like your bowl of soup, and you have like an alphabet soup, right? You have like little letters. You have like an A over here, a B over here, a C over here, D, E. Like you have an alphabet soup. You have like these are supposed to represent points, right? You have your alphabet soup. So this is like a discrete approximation to the entire space. But you have your alphabet soup. You have all of your letters floating in the soup and everything else that you see in the soup. And then you're going to take your spoon, you're going to mix it around, and you're going to look at the before and after picture. And what you will find is that one of the letters, let's say D, remains the same where it was. Now, of course, in real life, because this is like a discrete approximation, it might move a little bit. And so it means that maybe the true point were somewhere in between those two. You cannot actually draw a picture of every infinite point. So this is like an approximation, but you get the idea. This is what you would see, that if you have like a before and after picture, maybe you can even do this experiment in real life. Like take a soup, fill it in with like hundreds of letters in a way that you can tell them apart, mix it up in any complicated way that you want, and then look at the before and after picture and everything moves. Except for, well, I should not say everything moves. There's going to be at least one point that will not move, at least one. And one is the best that you can do. Well, one, I should say, is the worst that you can do. Because imagine that you're just taking a spoon and you're moving everything around the circle. So then everything's going to rotate around the center, right? You can just imagine taking the spoon and rotating this around the center. And then everything's going to rotate around the center except the center. The center will stay fixed, but everything else moves. So in the worst case scenario, you can move everything except for that one point in the center. So that's the really surprising consequence of this theorem. Like, it's really surprising, but that's what it says. So we're going to prove this theorem. It's surprisingly easy to prove, and we need a lemma to prove this. So the name of this lemma, so we have a lemma here. It has a name. It sometimes goes by the no retraction theorem. So Moncrief calls it the no retraction theorem. So this is what it says. There is no continuous map, let's call it R, that maps the closed unit disk to its boundary and keeps the boundary fixed, i.e. R of x is equal to x for x on the boundary. So the picture here is we have our closed disk, so that's our closed disk, and we have the boundary going around the disk. Right, so that's the boundary going around the disk. Now you can of course do something silly. You can of course map the disk to the boundary with something silly. You can just map all of it down to a single point 1, right? You can always map it. You can do a constant mapping. You can do a constant mapping where you say that every single point in the closed disk should be sent to 1, and then you have just produced a continuous map from the disk to its boundary. But that's not what we want to do here. Here we want to keep the boundary fixed. So that means we want to find a continuous map that will keep this blue piece fixed, and then every other point is being mapped somewhere into the blue piece. And we're saying there is no continuous function that will do it for you. In a way, it kind of makes sense. How do you take points in here? Like, if the origin was missing, let's say if the origin was missing, it's clear how to do it. You take every point and you just map it like this outside until it hits the boundary, right? As long as you stay away from the origin, you just map every single point outside. But then the question is, where does the origin go? And there is no continuous way to do it. So if the origin was not there, you can come up with what is known as a retraction, right? You're sort of retracting it. It's sort of like, when you have like an antenna, like if you have like a radio antenna, you can like retract it back so it kind of goes back in. So this, like the base of the antenna does not move and then everything retracts back. So this is why it's called a retraction. We're saying there's no way to retract the disk to its boundary. That's basically what it's saying. Like if you, intuitively it makes sense, but of course, how does one prove it? And if the origin was missing, then it's clear how to retract it. As long as you stay away from the origin, you just go in the outside directions and you just map it to that boundary circle and that will work for you. But by including the entire closed disk, the no retraction theorem says that's not possible. So let's justify the no retraction theorem. It's actually surprisingly simple. So here's how we do it. So let I be the inclusion map. So this is I of x is equal to x. And R is the retraction map from D2 into S1. Okay, so that we have these two. And R of x is equal to x for x on the boundary circle. So we're not saying that R of x is x, we're saying that R of x is x as long as you're on the boundary circle. So that is what is the definition of a retraction. So we're going to get a contradiction out of this. We're going to say that if you have a retraction mapping from the disk to its boundary, you're going to get a contradiction out of this. So how do you do this? So here's the way you do it. So you're going to observe that if you do R composed the inclusion mapping from S1 to S1, that this is equal to, so then R composed this is equal to the identity on S1, right? Because what happens? If you take a point on the unit circle, the inclusion map maps the point x to itself, and then the retraction map by assumption, if that point is already on the unit circle, which we're assuming it is, the retraction map maps it to x again. So this composition gives us the identity on the circle. So actually, let's draw a picture like this. S1 by the inclusion mapping. So let's write it like this, S1 comma 1. We pick a base point. S1 comma 1 gets mapped to D2 comma 1. Then we have a retraction that maps it to S1 comma 1. And then we have an identity mapping from S1 to S1. So we have this diagram commutes. That's what we're saying. If you go I and then R, that's the same thing as doing the identity. And now we're going to apply the fundamental group, right? So now apply the fundamental group functor. Fundamental group is a functor, and one of its properties is that it preserves commutative diagrams. So then we have the fundamental group of S1, being mapped by I star. That's the induced homomorphism on the fundamental group. Pi 1, D2, 1. This is R star. Pi 1, S1, 1. And then here you have I star. I star. Okay? Now let's write down our knowledge of the fundamental groups. This one, so this is the identity. The induced map on the identity is the identity of fundamental groups, right? That's the property of the functor. It preserves the identity. So this is the identity again. This is now the identity on fundamental groups. And what do we know about the fundamental group? We know that the fundamental group is isomorphic to the integers. So we can put the integers here, and we put the integers here. And what about this? This is the fundamental group of the disk, but the disk is contractible, right? This is trivial. This is just a group containing just 0, you can say. It's the trivial group. This is because the closed disk is contractible. It has the same homotopy type as a single point. So its fundamental group is trivial. And this is impossible, right? This diagram is a contradiction. Why is it a contradiction? Well, because we're saying the identity map, so the map that maps the integers to the integers in the identity fashion, so an integer is mapped to itself, is equal to this composed with this. But this is the 0 map, right? Just take any integer, right? Just take any integer n. n has to go to n. That's what the identity map says. But this mapping is the mapping into the 0 group. So this is mapping to 0, and then 0 gets mapped to 0, right? Because the identity element gets mapped to the identity element in the group. So this just goes to 0. And that's the contradiction. N is supposed to go to n, but when you go the other way around this diagram, that means n is being mapped to 0. And you have a contradiction out of that. So that's the no retraction theorem. So it's kind of interesting how you prove it using the fundamental root. So now let's return to Brouwer's fixed point theorem. So Brouwer's fixed point theorem. So here's the way it goes. It says that if f from D2 to D2 is a continuous map, then there is a P, a point inside the closed unit disk, so that f of P is equal to P. And here's the proof. And the proof is just a few lines. But of course, it's only a few lines because all of the heavy work has been done on the fundamental group. This is really what makes it possible. So here is Brouwer's fixed point theorem. You're going to assume there is no fixed point. Okay, we're going to assume that there is no fixed point. And we're going to construct, okay, so f of x is not equal to x for any x in D2. And now here's what we do. So here's a picture. We have a point x. So we have a point x somewhere, right? We have a point x. And then f of x is somewhere else. It's not equal to x. It's somewhere else. Let's say it's over here, f of x. So the picture is we can draw a ray from f of x to x because you have two different points. So you can draw a ray from f of x to x until it intersects somewhere on the circle. So now you draw a ray from f of x to x until it intersects a point on S1, on the boundary. And we call that R of x. We're going to call that point R of x, where it intersects. Okay? And what we should observe is, that if x is already on the boundary circle, then R of x is itself. Why? Well, just look at the picture again. The picture is going to tell you what happens. So here's your circle. So we're saying, suppose that x is already on the boundary, and f of x is somewhere else. Let's say it's here. It does not matter. F of x can also be itself on the boundary. It does not matter. It does not matter where it is. F of x can be there. And you're going to do the same thing. You're going to, from f of x, you're going to draw a ray until x and find where it intersects the boundary circle. But that's already at x because x is already on the boundary circle. So the function, so we have a function, so we have a continuous map, R, that takes every point in the closed disk and it assigns that point somewhere on the boundary circle. Now, small questionable step here. Why is this map continuous? Well, I think it's believable in the following sense, because if you had a small little perturbation, if you were to slightly move x to a different point, this is sort of the way we check continuity, then f of x, because f of x is continuous, it will slightly get misplaced from where it is. And then when you redraw this ray, will be close to where the other ray was. So small changes in x produce small changes in R of x. Not a rigorous proof, but writing a rigorous proof for this pretty clear fact would be a massive distraction from the main idea of the proof. So kind of need, like, we need a we're kind of trying to focus on the main idea. Focusing on why r of x is a continuous function is sort of a distraction from what's more important. So okay. Furthermore, r of x is equal to itself if x is already on the boundary circle. So thus, r from D2 to S1 is a retraction of D2 onto S1. And this contradicts the no retraction theorem. Right? The no retraction theorem says there's no retraction from D2 to S1. And that's the contradiction right there. So very nice proof, very short, but it's only made possible. Well, it uses the no retraction theorem, but the no retraction theorem is only made possible because of all of the hard work that we have done using the stuff with homotopy and fundamental groups and all of that. And Moncrief goes on to show a very interesting application to linear algebra. I do want to make a comment before I finish on this Brouwer fixed point theorem. We're going from D2 to D2, but you can also do this from Dn to Dn. The Brouwer fixed point theorem works for an n-dimensional disk as well. However, we do not have the tools to prove that because we only have the fundamental group. You can prove it using higher homotopy groups like P1, P2, P3, or you can use it using homology groups. So in Topology 2, we learn about homology groups, and there you can make this proof work. And in fact, it's almost the exact same proof. It goes almost exactly the same way. You show that you kind of create the analog of the no retraction theorem for the n-dimensional disk all over again, and it's the same proof. But the no retraction theorem needs to be justified using other means that generalize to higher dimensions. So that's the piece that is missing. So it is true, but it does. The current methods that we have do not allow us to prove it. So I do want to show you an interesting application of this in linear algebra, and you can find this in Moncrief's book. This is a theorem. So he calls this the Frobenius theorem, and it makes sense because there's a theorem in matrix algebra called the Frobenius-Perron theorem. It's actually a theorem in applied mathematics. Like, you do not really use it that much in pure mathematics as far as I know. The one place it comes up is when you're dealing with these things called Markov chains. And when you're dealing with Markov chains, there's this thing called the ergodic theorem for Markov chains about how they move around randomly and how much time they spend in every single state as they move around. And somewhere along the lines, this theorem is being used. It's some theorem about matrices, and a Markov chain has an associated matrix to it. So it's some kind of theorem about this. So if you kind of look it up on Wikipedia, you will notice it's very similar to what Moncrief writes, but it's a little bit different. The actual Frobenius-Perron theorem says that you can find an eigenvalue equal to exactly 1, whereas the theorem that is presented in the book is a little bit different. So this is the Frobenius theorem. It says that if A is a matrix that's 3 by 3, and the numbers of the matrix, I'll write it like this, Aij. So Aij just represents the number at row I, column J. They are all positive. So you have a matrix. So this is, you can call this maybe a positive matrix. And let's emphasize a strictly positive matrix, because as we know, positive in math often means non-negative. So then we say strictly positive. So A is a strictly positive matrix. Then A has a positive, strictly positive eigenvalue. The Frobenius-Perron theorem says that you can make the eigenvalue be equal to 1, but this is the version that's presented in Moncrief. This is stated for 3 by 3 matrices, but I can imagine that this can easily be generalized to higher dimensions once you have the generalized Brouwer fixed point theorem. But it can only, with the current tools that we have, we can also only do it for a 3 by 3 matrix. Now, the reason why you might say, well, what's the big deal here? Why not just find the eigenvalues? Well, the problem is there is no simple formula for the eigenvalues of a 3 by 3 matrix. There is a formula for the eigenvalues of a 2 by 2 matrix, if you know all of the numbers in the matrix. But even that formula is a little bit messy. But I've never seen a formula for the eigenvalues of a 3 by 3 matrix. I imagine it has to be unbelievably messy. So that's clearly not the way to do it. You want to use some kind of other argument to justify why it has a positive eigenvalue. Actually, we were joking about the fundamental theorem of algebra. A matrix, so if A is a matrix, is a square matrix with an odd number of rows, columns, then it always has at least one real eigenvalue. This is not difficult to prove. This is basically the fundamental theorem of algebra, right? It kind of fits nicely with what we've been doing. Fundamental theorem of algebra, how do you find the eigenvalues of a matrix? You look at the determinant of lambda I minus A. And this is a polynomial in lambda of degree n. So if A has an odd number of rows and columns, then the determinant of this would be a polynomial in lambda whose degree is an odd number. And then by the fundamental theorem of algebra, this has roots. Some of those roots might be complex, but they cannot be all complex numbers. Because if you have one complex root, right, if you have, let's say, lambda equal to 3 minus 4i, then the conjugate of it would also be a root. They come in pairs. And since they can be paired together, there's an even number of pairs. But the degree is odd, and so it means that there has to be a real root. So there must be a real root. So that's kind of interesting. It's very interesting. It connects with what we were just talking about, the fundamental theorem of algebra. It's like an unexpected connection that we just talked about that a while ago in the same lecture, and it comes up again all in the same discussion. But here, it's not about that it has a real eigenvalue, but it has a strictly positive eigenvalue. So that's what it is. And the proof is very nice. It's a topological proof. Here's the way the proof goes. I am not sure how Frobenius proved that himself. Would be interesting if he used the topological proof. I do not know, but here's the way the proof goes. You're going to let O represent the following set. This would be x1, x, y, z, where x, y, and z are bigger than or equal to 0. Okay, so this is the octant. Coordinate axes so the octant, the thing that's facing towards us. So that's the octant. And then let x be the intersection between the closed octant and the unit sphere. Okay, so you intersect the closed octant with the unit sphere. So you have a unit sphere sitting inside three-dimensional space, and you're going to look at the part of the unit sphere that is facing towards you. So as a picture, it would go something like this, right? So as a picture, that's how it's going to look like. It goes towards you, right? So that's like a cap of that unit sphere, right? The part that's facing towards you. So then observe that X is a topological closed disk. So we're saying X is homeomorphic to D2. So that means, so hence, Brouwer's fixed point theorem applies to X. Right? It applies to X. So here's what we do. So construct the map f from X to X as follows. So f of X is equal to, so we're going to do matrix multiplication on X. Okay, matrix multiplication on X. So X is a point in R3. This is something in R3. This is the two-dimensional sphere sitting in R3. And you're taking something that they have in common. So X is a point with 3 coordinates. So the way this is calculated is you have to interpret X as a column and do matrix multiplication. Now, the problem is that this is not necessarily in X. To be in X, it has to be in the sphere. So that means the sum of squares has to be 1. When are you on the sphere, on the unit sphere? When the sum of squares is equal to 1. Here, the sum of squares is not necessarily equal to 1. So the way you make it be in the unit sphere is you turn it into a unit vector. And the way you turn it into a unit vector is you calculate the 2 norm. This is the sum of squares, and you divide AX by that. And now you have something in the octant and in S2. Maybe to add a little bit of detail, if X is in X, then X has 3 components where the 3 components are all positive. So the components of AX are also all positive, because the matrix, by assumption, all of the numbers in the matrix are strictly positive. So when you do matrix multiplication, you're just adding strictly positive numbers together. So this is a strictly positive number. It's not equal to 0, so you're allowed to divide out by its norm. So this is something that's strictly positive, and you renormalize it. So then look what happens. It's in the octant, because all 3 of these are strictly positive, and it's in the disk, because it's been renormalized to have unit lengths. So this is a map from X to X, and it's a continuous map, because linear maps are continuous, and you're dividing by something. There's no problem with division, because you're never dividing by 0. So this is a continuous mapping. And now, to complete this, you would say that by Brouwer's fixed point theorem, there is a vector, let's call it V in X, so that f of V is equal to V. So if you just open up what that means, A of V is AV divided by AV2 is equal to V. And now if you clear denominators, we get that AV is equal to the scalar AV2V. And whatever this is some kind of number which you can call lambda. That's some positive number. So V is an eigenvector. It's an eigenvector. All of these are strictly positive. To be an eigenvector, it cannot be identically 0. It's an eigenvector with strictly positive eigenvalue. Okay, so that is Brouwer's fixed point theorem applied to some matrix algebra. Very, very surprising connection. So we'll stop here. That's some nice, interesting. So we can call this, so in math we call these applications. In pure math we call these applications. So we've just did some applications of the fundamental group. Of course, in pure math, when you say applications, you mean applications to other stuff in math. But nonetheless, those are some very interesting applications.